Hi, I'm Gerardo Ibarra Vázquez and I'm gonna present you automated design of accurate and robust image classifiers with brain programming. Image classification is a research area which involves complex analysis of features, as in our media categorization problem, and demands reliable systems like face recognition. Deep learning with deep convolutional neural network has been among the most popular and successful methods for solving image classification problems. Evolutionary computation and swarm intelligence have mainly contributed in two manners. One is optimizing feature selection and optimizing DCNN architectures. However, recent studies have reported that adversarial attacks are a severe threat to DCNN because with a small perturbation intentionally created, they could manipulate the output from a model. In this manner, this adversarial attack has been proposed as optimization problems, that the objective is to find a perturbation that leads to an incorrect output. For example, for target attacks, the intention is to minimize the cost function J to specially predict the target class with a restriction of the norm of the perturbation to be less than or equal to a small value of L in order to be imperceptible to the human eye. In the other case, no targeted attacks maximize the cost function with respect to the original label to predict a different class, also with the same restriction to be imperceptible to human inspection. Contrary to DCNN, our brain-inspired computational model of the visual system, which pursues the imitation of the visual information processing that occurs in the brain. Brain programming is a hyperheuristic capable of automatically designing new algorithms by configuring functions to optimize complex model of the artificial visual cortex by adjusting the operation within this intricate structure. The artificial visual cortex has a defined hierarchical structure inspired by the human visual cortex that uses a set of atomic functions specialized to extract the image discriminant characteristics. It is a flexible algorithm framework that generates specific classification models due to the balance between the fixed template method defining invariant parts of the program which are not subject to variation and the part which can be adapted. Brain programming uses an evolutionary paradigm to evolve a population of individuals represented by the ABC template for developing image classifiers. The analytical part resides on the ABC where the high-level processes are defined to secure concepts like invariance and hierarchical visual processing. The synthetic part is in charge with heuristic discoveries through the application of genetic programming as the search method. Therefore, brain programming automatically improves the ABC structure to design accurate and robust image classifiers. Brain programming also uses an adapted methodology to avoid the unnecessary application of arbitrary or unplanned solutions within the algorithm to advance towards a more goal-oriented search. It is named hands-on artificial evolution. The reason is not to leave the methodology to discover the best solution when they have complex structures to evolve, but helping it with previous discovery would guide the search in a better direction. So the idea was to use the best solution discovered during previous searches as the initial population to set a new experiment to find a better solution. In order to design accurate and robust image classifiers, first we need to find competitive solution to DCNN in image classification. In this case, we use our media categorization problem and face recognition. Secondly, we need to analyze them in terms of robustness to adversarial attacks. We use two popular attacks for this task: the fast gradient site method and facial accessories perturbation. Therefore, we use a standard database to perform our experiments. For our media categorization, we use Kaggle R database for training and validating the models, and WikiR for testing. In the face recognition, we use a database, which is a celebrity faces image database on which we construct the training, validation, and testing datasets. First, regarding the face recognition problem, we show in Figure 4 the fitness evolution progress of brain programming in the training phase. It is seen that the most of the run converge to approximately 75% of the validation accuracy. Two runs achieve around 80% and one run obtain approximately 90%, as shown in Table 5. Hence, we can see that it is not easy to reach satisfactory solutions in the search space due to the complex structure of the ABC departing from random individuals, but it was possible to obtain an excellent individual. Therefore, we followed the hands-on artificial evolution strategy in which we select the best two individuals from each run to construct an initial population to search for new individuals. Figure 5 showed the fitness evolution progress of 5 runs from this strategy. It can be seen that the guide from previous experiment delivered an increase of up to 5% in the performance. The facial accessories perturbations infer that the attack is made with the targeted model knowledge to evade the recognition. In this manner, facial accessories are used to perform the attack, which in this case are eyeglasses frames. The advantage of facial accessories is that they can be easily realizable in real-world conditions. Hence, a set of eyeglasses frames is employed to physically realize the attack, ensuring that the perturbation effectively misclassifies more than one image. In order to find a perturbation that performs the attack, the following optimization problem needs a solution, where the perturbation R would maximize the softmax loss value to minimize the probability of the class. To guarantee the generality of the perturbation, we need to look for complex models that can cause any image in a set of input to be misclassified. Hence, the attack requires a set of images and finds a single perturbation that optimizes her objective for every image in the set of images. Here in Table 6, we show the outcome of each model for the clean images and when it is applied the eyeglass frame perturbation to the training, validation, and testing datasets. Each method presents its accuracy to each dataset. We observe that ResNet surpasses brain programming in all sets of clean images. However, as we add the eyeglasses frame perturbation to all sets of face images, the adversarial attack effect becomes enormous. It is shown that ResNet completely drops its outstanding performance as the eyeglasses frame is present in the face images, making almost every face image in the three datasets evade the recognition. Additionally, Table 6 shows a two-sample Kolmogorov-Smirnov test between each pair of prediction confidence at each stage between ResNet and brain programming. When H is 1, if the test rejects the null hypothesis at the 5% significance levels and 0 otherwise. Hence, all the prediction confidence at each stage between both methods denoted significant differences by rejecting the null hypothesis. In the R-media categorization problem, we employed the most widely used method for computing perturbation due to its easy implementation, the fast gradient size method. It increases the loss function of the classifier by solving the following equation, where it computes the gradient of the cost function around the current value of the model parameters theta with respect to the image x and the target label. It uses the sine function to ensure that the magnitude of the loss is maximized and epsilon is a small scalar value that restricts the norm of the perturbation. We see in Figure 2 examples of perturbed image at different scalar value. We observe that even using a scalar value of 32, it is almost imperceptible how the image was modified. Table 7 presents the results of the art media categorization experiment. It shows that ResNet has surpassed brain programming in almost every class when it is validating the model except for the painting class. However, as we add the perturbation to the validation images, the effect of the adversarial attack becomes more notable. It is shown how the performance of ResNet could be deteriorated. In the worst case of engraving color images, there is a drop in performance from 97% to almost 3% of classification accuracy. On the other hand, PP preserves its performance on all experiments even when we add the strongest perturbation of epsilon equals to 32. Hence, if we take a look at the best performances of each one of the models, marked in bold numbers, PP outperforms ResNet. In the testing phase, we have that brain programming obtained notable better results in classes like painting, painting landscapes, and drawings. In contrast, ResNet obtained superior performance on engraving grayscale, engraving color, and iconography. Regarding the sculpture class, brain programming matches the performance of ResNet with a difference around 2%. Then again, the vulnerability of ResNet to the perturbed images is a bit disadvantaged. Its performances fall abruptly in all classes, meanwhile the brain programming output remains steady. As conclusion, we observe that adversarial attacks are a severe threat to the security of deep convolutional neural networks in image classification. Also, brain programming demonstrates to automatically design ABC models capable of competing with DCNNs in two different tasks and safeguard the prediction's integrity by remaining steady in its performance. Additionally, we validate the hands-on strategy beyond a pure random initialization that help to get out from the local minima to discover better solutions. Finally, this work innovates by introducing the assumption of an attempt to fool the image classification system and highlight the difference between a renowned DCNN ResNet and the ABC models generated by brain programming. Thanks.